Hey everyone, and welcome. Have you ever found yourself just staring at a complex electrical circuit, completely lost on where to even start? Well, today we're going to pull back the curtain on a technique that's like a magic wand for circuit analysis, turning something totally complicated into something beautifully simple.
Yeah, does a circuit diagram like this ever just freeze your brain? You get a case of analysis paralysis. All those resistors, loops, and nodes can feel pretty overwhelming, especially when you're just trying to figure out what's happening at one single point. Trust me, it's a common feeling.
But what if I told you there's a way to take that entire messy network and swap it out for something incredibly straightforward, something anyone could solve in like 2 seconds flat? Just look at this. On the left, that's our big, complicated problem. And on the right, that's what it can become. And get this, from the perspective of any component you plug into those two terminals, what we call the load, these two circuits behave exactly the same. So what is this electrical magic?
Well, that magic has a name, Thevenin's theorem. So let's dive in. Seriously, think of this as your secret weapon, an elegant shortcut that makes circuit analysis so much easier.
The core idea is right here. Any linear circuit, and that covers most of what you're going to run into, can be boiled down to a simple, predictable equivalent. The key word here is any. It doesn't matter how tangled it looks. That's what makes this so incredibly powerful.
And what does this simple circuit look like? Just two parts. A single voltage source connected in series with a single resistor. That's it. All that complexity from before is just gone, distilled down to just two simple components. Okay, so if every complex circuit can become this simple little pair, the big question is, how do we find the values for that voltage source and that resistor? There are two key ingredients, and they have special names, the Thevenin voltage and the Thevenin resistance. Here's the breakdown. On one side, we have the Thevenin voltage, or VTH for short. You can think of it as the circuit's raw potential. It's the voltage you'd measure if you just put a multimeter across the two open points. On the other side, we have the Thevenin resistance, or RTH. This is like the circuit's internal opposition, what it feels like when you look back into it. Together, these two values perfectly mimic the original network. Right, that's all great in theory, but how do we actually get our hands on them? How do we calculate VThev and RThev from our original complicated circuit? All right, let's get practical.
We're going to walk through a step-by-step example. This is where all the theory becomes a real tool you can actually use. So, let's solve one together.
Here's our roadmap. It's a simple 4-step process. First, we'll isolate the part we care about by removing the load. Then we'll find VTH, then RTH, and finally, we'll draw our new simple circuit and get our answer. See? Not so bad.
First things first, we need to decide what we're analyzing. Let's say it's one specific resistor. We'll call that our load. So step 1, we just pluck it right out of the circuit. This leaves two open terminals, which is perfect because it lets us peek inside and see how the rest of the circuit behaves from that exact spot. Now with the load gone, we just calculate the voltage across those two open terminals we just made. And that voltage reading? That is our Thevenin voltage, VTH. It's the natural voltage potential the circuit produces at that point, just waiting for something to be connected. So he'd do a little bit of analysis on what's left on the circuit, maybe use the voltage divider rule or something similar. And for the example circuit we're working through, that calculation gives us a Thevenin voltage of 6.67 volts. Perfect. That's our first ingredient locked in. Next up is our Thevenin. To find this, we need to look back into those same open terminals and find the total resistance. Now here's the crucial part. We do this with all the power sources turned off. For a voltage source, that means we replace it with a short circuit, basically just a wire. So again, we'd look back into the terminals and calculate the total equivalent resistance. This usually means combining some resistors in series or parallel. For our example, this calculation gives us a Thevenin resistance of 6.67 ohms. And just like that, we have both pieces of our puzzle. And now for the final step, the best part. We take our two calculated values, Vthin and Rthin, and we draw our brand new Thevenin equivalent circuit. Then we can plug our original load resistor back in and easily solve for the current or voltage across it using simple Ohm's law. No more complicated loops. So after all that work, what do we have to show for it? Let's get to the big reveal and see the real payoff. And here is the transformation. That complex circuit we started with, a 10-volt source with a 10 and 20 ohm resistor, is on the left. And on the right is our new, simple equivalent, built with the values we just found. The magic is that for any load you connect, the circuit on the right behaves exactly like the one on the left.
It's incredible.
So why does all this matter? Well, Thevenin's theorem is a fundamental tool for simplification. It lets you take a really complex network and boil it down to its two most essential components, its potential, V-thir, and its internal resistance, R-thir. This makes analyzing different loads incredibly fast, and it's an essential shortcut for anyone working with electronics.
Now that you have this powerful tool in your back pocket, you have the ability to look at a complex network and see the simple equivalent hiding inside. So the only question left is, what will you analyze first?
Thanks for watching.